Hello and welcome. Today is the second day of the 6th week of this course, and we were discussing about different types of lasers, and today we are going to start with chemical lasers. So as the name suggests, chemical laser, it deals with some chemical reactions which ultimately leads to some products which provides the states that ultimately can give laser action. So two different types of chemical lasers we will discuss. One is iodine laser, and the second one we will talk about an excimer laser. Okay, so let's start with iodine laser. So first, let's look at the you know the system. So iodine laser, it deals with the energy levels of iodine atoms. Okay. Now getting only iodine atom is difficult. So you have to do something that you produced iodine and then you exploit the energy states of that iodine atom that is produced in either excited or ground state, whatever, and then get your laser output. Okay. So this is what it is done. So the population inversion in this case is created directly through an exothermic chemical reaction, or or it can be any other chemical mean. Okay. So what you do, you take a compound containing iodine. So for example, here we have taken C3F7I. Okay. So for that matter, you can take fluoroiodocarbon or iodohydrocarbon. Now this molecule you have to excite so that it gets dissociated. So your aim is finally is to have the C-I bond dissociation. Okay. So you have to go from here to C and I. So this C3F7I is excited by some photon. Okay. So that is shown here. H nu P is the pump photon, and this pumping will give rise to the dissociation of this molecule, and it will create two different species, C3F7 and I star. And if you look at the energy level diagram, you will see that first absorption of light, it takes the molecule beyond the dissociation limit. And when I talk about this dissociation limit, essentially I am talking about Ci bond dissociation limit. Okay. So CF bond can dissociate also, but that requires totally different amount of energy. So the energy that is provided, it will break only the Ci bond, because CF bond needs much different energy compared to Ci. So once this Ci bond is broken, then the iodine atoms that can be produced either in its ground state or in excited state. So here this P3/2 is the ground state, while P half is the excited state. This picture is not very clear, so I apologize for that. But this is the P half system, and the ground state is P3/2. Now the iodine can be produced in either of these states. Okay. Most of the time you will not be able to control it, like control the quantum yield of I star. So the iodine in the excited state is written as I star. Okay. So this is the excited state iodine atom. corresponding to P 3 by 2, sorry, P half. So you cannot control how much P half or P 3 by 2 will be produced, but different molecules will produce iodine atom due to Ci bond dissociation with different quantum yield. So you choose a particular molecule which has a very high quantum yield for I star. So one of such molecule is C3H F7I, which gives this I star in high proportion, at least decent proportion. Now this I star is a metastable state. So the initial pumping will create this iodine molecule in the excited state, that is, it will form I star, and more I star will keep accumulating. So if you consider these two levels, this level will keep hosting I star molecule, while this level is nearly unoccupied. Now this P3 by 2 level, that is the ground state iodine, it decays here to this level through recombination. So you break the Ci bond, so the other fragment is also there and this guy is also there. So they are within the system, right? So they can again meet and recombine. So the moment they recombine, what they will do, they will come down to this state, right? So they can absorb the this particular transition will give me my laser output, and the wavelength corresponding to this laser output is 1.315 micron. Okay, so this is the whole procedure given in this reaction scheme. So you essentially have this particular step responsible for the laser action. Okay, now some practical consideration. This molecule C3F7I is stored in some small ampule, and introduced into the laser, in front of laser, and the pressure is kept between 30 to 300 millibar, and you ultimately achieve the lasing action. So I have already discussed this part. Now what is the advantage of iodine laser? So the advantage is in the fact that the active medium is comparatively cheap, right? So these halides are quite abundant. Okay, so compared to this inert gases, it is a lot easier to get this molecule, and so therefore it is it can be cheap compared to other active mediums that we deal with. The next that we are going to talk about is excimer laser. Okay. So this excimer laser, or for that matter this excimer, what is this excimer? If I expand this term excimer, it says excited state dimer. If it is like dimerization of the two same unit, then it's an excimer. If the two components are different, then this is like a complex formation at the excited state. So this is called excited state complex or exciplex. Okay, so an excimer is an exciplex essentially. Only thing is that the constituents are same. And in excimer laser, this exciplex is the active medium. Okay. Now, this is exciplex is an excited state complex. That means that it does not exist in ground state. So this complex is formed only when these components are excited. Okay, then they do reaction and then they form the complex. But in the ground state, they are, not together. They don't have any bond between them. So if I look into the energy, potential energy diagram, then it will look like the ground state there is no bond. So if there is no bond, then the ground state is not a bound state, right? So the it will look like a dissociative state or unbound state. An unbound state looks like this. So this is my ground state for this system. Okay, and when I excite them, okay, so I bring in a photon and the molecules here, they get excited and there they form the complex. That means the moment they are forming a complex, that means they have a bound state, and that is given by this. So this corresponds to my exciplex. It can be excimar also, okay, and this is ground state, which is unbound state, which means two constituent A and B, they are two separate entity. Here you have AP. So this is the concept of exciplex. Okay, so how this exciplex can be formed? Exciplex can be formed by giving electrical discharge. Okay, so suppose I have two different gases and I put electrical discharge, then these two molecules will be excited and form a complex, and that is my exciplex. So let's look at this problem a little bit in detail, taking some example. So let's take an example of a system comprising of krypton and fluorine. So krypton and fluorine, they do not react in the ground state, but when they are excited, okay, so when they are bombarded with this electron, so due to electron impact, the krypton becomes krypton plus and fluorine becomes F minus. Now this F minus and Kr plus, they are excited state, and at that condition they are forming this complex KrF. Okay, and this is shown in this diagram. So this is the energy level diagram of the ground state of krypton and fluorine, where they are not interacting, while there they are forming and forming a complex, and they are already at an excited state. Now this excitation was created by electric discharge, right? So due to electron impact, this is formed. Now they will not be stable here, right? That is not a stable geometry. It's not a ground state. This is an excited state. So they will come back. When they come back, they again are dissociated, and when coming back, they will emit the photon, and that's my laser output, and that corresponds to 248 nanometer, which falls in the ultraviolet region. So this excimer laser, particularly this krypton fluoride laser, is a good source of UV light. Okay. Now in krypton fluoride laser, you also find helium. Now helium in this particular case doesn't play any role. So like you have seen earlier helium neon laser, so there helium and neon both are playing some role. Okay. But here helium acts just as a buffer. Okay. So this part we have already discussed. Now a few important aspects of this krypton fluoride excimer laser, that this laser can be operated continuously without direct consumption of any active medium. Yeah, that is probably an unique thing. So far, whatever we have discussed, all the time I have been drawing like a cavity and putting an active medium. Here you do not have an active medium to start with. You create an active medium by giving electric discharge, which automatically breaks down, giving a laser output. And these excimer lasers are super radiant, and they produce pulse radiation with a duration of 10 to 20 nanosecond, and the rep rate can be 1 to 500 hertz. And the pulse energies can be up to a joule, and the peak power can be a megawatt, and the average power can be like 20 to 100 watt. Now these are not a very large number, but if you think about a source giving ultraviolet laser photons, these numbers are quite good, okay, because the UV radiations are already high, highly energetic frequencies, right? So the next thing that we will discuss is one of the most important lasers, which is dye laser. Okay, and in the very first class where we started discussing about this different types of laser, we put this laser in a different category. Now, dye laser, as the name suggests, the active medium is constituted by a solution of an organic dye. Okay. So which particular dye you use? The good thing is that there are many dyes that you can use for this purpose. And how many? I mean, it's like 200 or even much more than that actually. With every passing day, you get a newer dye which has certain properties which are better than their predecessors. So you can have different dyes fulfilling your purpose. But it is not that any dye you pick up, it can give you laser action. Okay, so you need to have certain conditions fulfilled, as we know, for any active medium that one can use for laser. Also, this there is a general requirement that these dyes which we can use for laser action, they should have an absorption band in the visible or near IR range, preferably in the visible range, and they have a fluorescence band which should be quite broad. Then we can exploit it quite well. Now here I have shown a figure which shows that what are the different regions of the spectrum that we can cover using dyes as active medium, that is in dye lasers. So you can see it goes all the way from near UV to near infrared. So you can achieve any wavelength between this range 350 to 1100 nanometer using dye laser. So all you need to have is the right dye and the right pumping source. Okay, so the most famous dye that is used in dye laser is probably rhodamine 6G. This is a commercial name, and the molecular formula for that is given here, and this is the molecular structure of rhodamine. Okay, so earlier we mentioned that like solid state lasers, this dye laser also gives much broader fluorescence spectrum, and that is good in many senses. and this broadening takes place due to the interaction of these molecules with the surrounding environment, and because they are freely moving around. Now this broadening can be compared to a continuum state. So what happens in case of the excitation of a dye solution? So a visible light will take the dye molecule from ground state S0 to the singlet excited state S1, and from there, from this S1, there will be rapid decay to the lowest vibrational level of this S1 continuum. Okay, and from there it will emit, and this emission can be used as my laser. Now just I think previous class or the one earlier to that, we said that this emission can take place from the lowest vibrational level of the excited state to different vibrational levels of the ground state. So you can see that it can come back here, it can come back here, it can come back here and here. So all this corresponds to different vibrational levels. Okay, so you can get an overall broad spectrum, and because it is a broad spectrum, I can do something to select my output wavelength, and I can have a tunability. Okay, so this is actually we write here explicitly that the fluorescence emission, which is resulted due to this downward transition from S1 to S0, is essentially a transition to a continuum, because we have several vibration levels at S1, S0. Now you utilize this particular fluorescent emission to act as the as a laser output. Okay, and of course this is only possible when there is a population inversion creation is there. So if it is possible to create population inversion, it will act as lasing system, otherwise it won't. For an example, a dye laser based on rhodamin 6 dissolved in methanol, it continuously tunable over this range. So what is this tunable? Whenever we say that okay, this is the range of tunability for any particular laser, what we mean is that okay, the emission spectrum is having this particular range, and I can select the particular wavelength and I can achieve a tunable laser source. So here the spectral line width is really broad, and I can select different wavelength within this range and get an overall tunable laser system. Now let's have a look at the experimental aspect of this. So how this is achieved? So the dye laser is taken in a seal in a transparent container. So either glass or quartz container, and this is excited by either using a flash lamp or using another laser. Okay, so most common excitation for dye laser is a pumping by a solid state laser like ND arc laser. In the visible, so ND arc we said like it gives like 1064 nanometer as fundamental light. Once you frequency double that particular 1064 nanometer using nonlinear optics, you get 532 nanometer, and that 532 nanometer laser light is used to pump the dye that we are talking about, say for example rhodium 6G in methanol, and the emission from this particular excitation is now taken and it is optical cavity is constituted by mirrors, and we create population inversion, and we get ultimately the laser output. So this is what it is shown here. So you bring the pump beam from this argon ion laser here, and you hit the dye cell which is kept right here, all right, and the fluorescence is shown by this green light. So that is that travels back and forth between this output coupler and this high reflecting curved mirror, and you can get the output from this output coupler. On your left down, there is an actual picture of a dye laser, and particular the region where the dye cell is kept is shown here. So the dye cell is kept here in this square kind of cuvette. Now, one thing is very essential, which is not shown explicitly here, but it's mentioned that the liquid dye is flowing. So actually, you can see that there are these tubes which helps the dye to circulate. So the dye solution does not stay stagnant in that dye cell, but it continuously flows. Why this is necessary? Because the organic dyes are very well known to undergo photo bleaching if they are continuously pumped. So in order to avoid the degradation of these dye molecules, you need to remove the excited dye very soon, so that we can avoid the degradation, photo degradation. So this dye solution is continuously flown, and if you want to get much higher output, then what you can do is you can further amplify this output that you get from this oscillator, and you can use a grating to select the particular output that you want, because this fluorescence spectrum is quite broad, and you would like to have a narrow band light coming out of your laser, and also you want to have it tunable. So if you have a grating, then you can select a particular wavelength out of that spectral window that your dye is going to give you, and get a narrow band but tunable laser. So so we have discussed in quite detail about several different lasers, solid state lasers, gas lasers, atomic and molecular gas lasers, ion laser, chemical lasers, and also this dye lasers. With this we will end our discussion about different types of light laser system. In next few classes, whenever it requires, if we are dealing with some other type of lasers, then and there we will discuss about that particular lasers. So we will come back again in the following class, and I thank you for your attention.